This is the video for exam practice session 8, and in this video we'll cover two topics related to machine learning. The first is naive Bayes, and the second is the perceptron algorithm. So the goal of naive Bayes, and also for the perceptron algorithm, is to classify your data. And what this problem entails is you have a bunch of data, and we'll call that data X, and we know that we have some function that computes the features of X and compiles it and makes it into a single feature vector f of X. And the goal of the naive Bayes algorithm and the perceptron algorithm is to find a classifier that and a way for going from f of X to your label, and we'll call that L. The way that naive Bayes approaches this problem is to model the data as a graphical model, and then to perform classification is just the same as performing probabilistic inference of finding the probability that the label is equal to a certain quantity or equal to a certain value given the feature vector f. So what this looks like is what the naive Bayes model looks like is you'll have a random variable for your label L, and then you'll have a feature vector, and you'll have a different random variable for each of the features in your feature vector. So we'll have F1, F2, and so on up until Fn if you have n features. And we have this as a graphical model where each of the features depend on the label L. So the key insight with this model is that it makes some independence assumptions. And specifically, the independence assumption that it makes is that each feature, or each pair of features, fi and fj, are independent conditioned on the label L. And this is for all ij not and ij not equal, I not equal to j. Okay, so now let's look at the problem that we're trying to solve. Here we're given two classes, so L has a domain size of 2, and they're shown as rectangles and dots. So one of the classes is a dot, and one of the classes is a square. And we have our data, which is shown by each of the dots. So each of our data points has a different value for F1 and F2. So we have two features. So our first feature is right here, and that's F1. And our second feature is plotted on this axis, which is F2. And then we have each of our data points for each of the two classes, and we want to determine whether or not they satisfy the naive Bayes modeling assumptions. And that specifically means that does this data satisfy the assumption that fi is independent of fj given the label L? So the way to approach this problem is we want to look at the points, and we can consider each label separately because we're interested whether they're independent given the label. So if we first look at this box right here, this box of points, we can see we want to determine if F1 is independent of F2. So the question is F1 independent of F2 given your label, and where your label is a dot or a square. We can see that in this case, for F1 to be independent of F2, the probability of F1 has to be equal to the probability of F1 given F2, and vice versa. Probability of F2 has to be equal to the probability of F2 given F1. So the way we can look at that is if we see this point and we know that F1 is equal to some value right here, then as a result, we know that F2 can be any one of these number of points, and it's equally likely to be one of these points. Similarly, if F1 takes on a different value, then F2 must take on any one of these points. And what we can see is when our data is a square like this, knowing F1 doesn't tell us anything about F2, and similarly, knowing F2 doesn't tell us anything about the distribution over F1. Therefore, we know that in this square of data points, F1 and F2 are independent, conditioned on that the label is a dot. So it's satisfied for this label. However, now let's look at this label right here. So here, if we know F1 takes on this value right here, so it takes on something like 4, we know that F2 has to be equal to, there's only one data point right here, and it has to be equal to something like 0.75 or whatever that corresponds to right here. Versus if we know that F2 equals 1 or something, then we know that F2 has to lie in this range right here instead. So therefore, knowing F1 tells us something about what F2 has to be. So therefore, F1 and F2 are not independent, because knowing F1 tells you something about the distribution over F2 and vice versa. So this assumption isn't satisfied for this label. So therefore, this set of data points does not satisfy the assumptions. Now let's move on to part B. So in this case, we have two squares. So we can see that in both cases, F1 and F2 are independent, because knowing F1 doesn't tell you anything about F2. And similarly, for this class, knowing F1 doesn't tell you anything about F2. It doesn't change the distribution over what values F2 will take on. So therefore, in this case, F1 is independent of F2 given your label for both labels. So therefore, the naive Bayes assumption is satisfied. Now let's move on to part C. So in this case, we actually have some overlapping points, but that doesn't really change what we need to think about, because we're always considering the labels separately, either the label of being a square or the label of being a dot. So in this case, in the case of the squares, it's this exact same thing as before, where we have a square. So therefore, knowing F1 doesn't tell us anything about F2. With the dots, it's slightly different because it's a rectangle, but you can still tell that if you, that just means that the range of F2 is between -1 and -1.8, and is equally likely to be one of these 5 points, regardless of the value of F1. And similarly, F1 is in the domain from about 0.4 to 1, and knowing F2 doesn't tell us anything about how F1 might change. Note that if you had like 2 points right here for some reason, and you had like 2 points right here, then they would be dependent, because knowing F1 would change your distribution. F2 would be more likely to be this point than the other points, versus if you knew F1 took on this value right here, then it'd be uniform again, versus F1 took on this value, it'd be more likely to be this point. So if this wasn't completely uniform and you had more than 1 point at each spot, then F1 and F2 would be dependent. But in the case where the points are as is, our naive Bayes assumption is satisfied, because F1 and F2 are independent. Okay, moving on to part D. This is pretty much the same case as before, except no overlap, where we have some rectangles, and knowing F1 doesn't tell us anything about the values that F2 will take on. Therefore, the naive Bayes assumption is satisfied. Next, we look at these last two examples. So in this case, F1 and F2 are not independent for either classes, because they don't take on this nice square shape, and where if you know F1, the values of F2 are going to change. So if you know F1 is in this range, then you know something about the distribution over F2. It has to be one of these three values, versus if you know F1 takes on this value, then you know that F2 has to be take on these set of values, and it'd be a uniform distribution over those values. And similarly for this rotated rectangle here, and for these points over here. So in both of these cases, the naive Bayes assumption isn't satisfied, because F1 is not independent of F2 given your label. They're dependent. So this is not satisfied. Okay, let's move on to question 2. So in this case, we are looking at Laplace smoothing, and looking at what happens to the likelihood of our data and our modeling capabilities as you apply Laplace smoothing. So a quick recap is if we want to estimate, before we run naive Bayes, we estimate our conditional probability tables in our Bayes net. And the way we do that is we can use maximum likelihood estimation, which is the same as Laplace smoothing with k equals 0. And what this looks like is if you want to estimate, for example, p of x, this is going to equal to the count of x, so the number of x's in your data set divided by your total number of samples. And this corresponds to maximizing the likelihood of your data if you use this value for computing p of x. So the goal of Laplace smoothing is to prevent overfitting to your training data. So for example, if one of your features is the word money, and you see the word money appear a few times in your spam emails, but you never see it appear in your ham emails, and you're trying to classify between ham and spam, then what this will do is it'll say that if money appears in your email, then it has 0% probability of being spam, of being ham, because you never saw that in your training data. So the way you account for this, because you want to incorporate some prior that your distribution is smooth. So what this looks like with Laplace smoothing is you might have p of x for k equals 5, and before up here this is the p of x, the maximum likelihood, or the same as k equals 0. But in the k equals 5 case, you'll have the count of x plus 5, or plus k, divided by your total number of samples, plus 5 times the domain size of x, so the number of values that x can take on. And what this is doing is that it's saying that for every possible outcome x, you're pretending that there are 5 additional outcomes in your data, and instead estimating the probability using that distribution, where you have 5 extra outcomes for every possible outcome. 5 extra instances of every possible outcome, and you use that to model your probability distribution. So a simple example of that is if you have a coin flip and you're trying to model, you see tails, 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 and you want to modify, you want to estimate what is the probability of heads. Then if you use maximum likelihood estimation, your probability of heads would be the count of heads, which is 0, divided by 3. And so that would be the maximum likelihood estimate. However, it's very possible that the probability of heads actually isn't 0, because you might have some prior that it's actually a coin and it has some non-zero probability of being heads. And so what you do if you had k equal to 5 is that you'll say there are, you'll add 5 outcomes of tails and 5 outcomes of heads. And the resulting estimate for the probability of heads will be 0 plus 5 plus divided by 3 plus 5 times 2, because there's 2 possible outcomes, tails or heads. And so the result will be 5 over 13. And the probability of tails will be, will then be 8 over 13. Okay, so in this question, we are considering 3 cases. One is which we have Laplace smoothing with k equals 0, which is the same as max likelihood. One is k equals 5, which is kind of what we saw right here. And one is when k equals infinity. And the case when k equals infinity is what you would do is you would take this equation, except have the 5 be k, and take the limit as k goes to infinity. So in that case, what you would get is these terms would not be used anymore because you have this term right here, and when you take the limit as k goes to infinity, then you get that the probability of x for k equals infinity is equal to 1 over the dimensionality of x. So this is actually exactly just the uniform distribution. So this is saying that all of your outcomes are equally likely regardless of what your training data is. Okay, so now let's consider the problem. So we are given a Bayes-net, and and we are considering GA and GB. So these are two different Bayes-nets that we're using to model our data. And we're interested in the probability of our training data, which is simply the product of all of the probability of each training example according to the modeled Bayes-net. And then we have different notations. So LA0 will be the likelihood of the training data with k equals 0. On this graph, L5A will be k equals 5, and so on, and similarly for graph B. So going back to this example right here where we have a coin flip, if we wanted to calculate the probability of our data, in this case, the probability of our data would be, so L in terms of the ML case, where our training data is TTT, tails, 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 is going to equal to 1 to the third, which is where 1 is the probability of tails, times 0 to the 0, because there are 0 heads. So this is just going to equal 1. So under this model, the probability of our training data will be 1. Versus under this model, where our training data is tails, 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 and we modeled probability of heads is 5/13. In this case, the likelihood of our data for k equals 5 will equal 8 over 13 to the third times 5 over 13 to the 0. And this will just go to 1, and the result will be 8 over 13 to the third. So note that the probability of our training data is going to be higher when we don't use any smoothing, because that's using the maximum likelihood estimate, versus when we do smooth, the probability of our training data goes down, but the benefit is we might have a smooth distribution that we can achieve better test accuracy on. It might be closer to the actual distribution on our Bayes-net for the test examples. Okay, so in this case, LML is greater than LK equals 5. However, if we were considering the likelihood of our test data, it might be true that actually LK equals 5 is higher on our test data, but we don't have access to our test data. We only have access to our training data, so that we can't tell that. We can't guarantee that. Okay, so in part A, we are considering LA0 versus LA5. So this is saying what is the likelihood of our training data for k equals 0 versus the likelihood of our training data versus with k equals 5. So in this case, k equals 0 is the same as our maximum likelihood estimate, whereas k equals 5 will be a smoothed version of our maximum likelihood that has a smoother distribution. It's closer to uniform. And therefore, the likelihood of our training data is going to be higher for k equals 0 because it's not smoothing, it's exactly fitting the data and maximizing that likelihood. So this is true. And it's going to be greater than or equal to, because it's possible that if the data is exactly uniform, then the smoothed version is going to be the same. So it's possible that, therefore, it's possible for the likelihood of our training data to actually be the same for k equals 0 and for k equals 5. Okay, now we are considering using just graph A with k equals 5 versus k equals infinity. And as before, it's possible that these are equal to each other, because if our data is just a uniform distribution, then estimating with k equals infinity will be the same as estimating with k equals 5. However, if our data isn't the uniform distribution, then k equals 5 is going to more accurately fit our training data. And so therefore, the likelihood of our training data is going to be higher, because this is actually trying to fit our data in some way, whereas k equals infinity is just returning the uniform distribution. So the probability of our training data is going to be higher for k equals 5. Note that this doesn't actually mean that the individual probability values of our BaseNet, like these conditional values, are going to be bigger. It just means this value up here, the product of the probability of our training data, is going to be larger, not the probability values themselves. For example, all of the probability values for k equals infinity are going to be uniform, and if you have something, some probabilities that are less than uniform for k equals 5, because that data appeared less frequently in your data, that probability value will be less in your BaseNet, but those outcomes will appear less frequently in your training data and therefore will be weighted less, and the probability values that are higher will be weighted more, so therefore the net outcome will be that the probability of the training data will be higher because it's modeling that data. Okay, now let's consider maximum likelihood on model B versus the uniform distribution, using the uniform distribution. So using maximum likelihood is going to model our data closer, and so therefore the probability of our training data is going to be higher for 0 versus if we model it with the uniform distribution. So this is definitely true that it will be greater than or equal to for using no smoothing versus a uniform distribution, which is complete smoothing. And it could be, again, it could be equal to if your training data is already the uniform distribution. Okay, so now let's consider the likelihood of A versus the likelihood of B with 0 smoothing. So what this is saying is the likelihood of your training data, the maximum likelihood using the maximum likelihood estimates, will the likelihood of your training data be higher for A, using model A, or for using model B? We can note that model A is making some independency assumptions, and it's making more independency assumptions than model B is making. For example, there are fewer arrows, and in this model, if you condition on this node right here, then each of these nodes will be independent of each other. And that assumption isn't made here. So we know that graph B makes strictly fewer independence assumptions. So therefore, model B could potentially model our data better. If our data already makes those independence assumptions, then these models would be able to equally represent that training data. But it's possible that our training data doesn't make this assumption that these variables are independent conditioned on this variable. So because of that, because model B has more expressive capability, it will be able to more accurately model the training data, and therefore the probability of the training data under this model, under model B, will be greater than or equal to the probability of the training data using model A. So therefore, this is the correct answer. Part E is similar. Actually, no, part F is similar, but let's start with part E. So in part E, both of these are modeling with k equals infinity. So as we saw before, these distributions are going to be the uniform distribution. So this isn't using any information from your training data. It's just assuming that all of the probabilities are equally likely. So therefore, the likelihood of your training data is going to be the same under both of these. So it's going to be equal to. So LA of infinity at k equals infinity is going to be equal to LB at k equals infinity. Next, let's consider part F. So in this case, we're considering model A with smoothing of 5 and model B with smoothing of 0. And we already know that model B is more expressive and might be able to model our data better than model A. Additionally, using k equals 0 means that we are going to exactly use the maximum likelihood estimate rather than trying to smooth our data. So therefore, LB of 0 is going to very closely model our data, model our training data, versus LA of 5 is going to not only induce some independency assumptions, but it's also going to smooth the distribution. So therefore, the likelihood of our training data with model B with 0 smoothing is going to be greater than or equal to the likelihood of our training data for with model A and Laplace smoothing at k equals 5. Note that this isn't true necessarily for our test data, but for our training data, this will be true. And it's possible that using model A with Laplace smoothing of 5 will better fit our test data because it won't overfit to the training data. However, in this question, we're just concerned with the likelihood of the training data. Okay, lastly, we are comparing using maximum likelihood with model A versus Laplace smoothing with model B. So what this is saying is we're going to use this less expressive, we want to compare this less expressive Bayes net with 0 smoothing to using a more expressive Bayes net with some smoothing. And we know that the likelihood of our training data will increase when we use model B, but it will also increase if we use k equals 0 versus k equals 5. And it's impossible to tell without knowing the specific training data which of these, which will make a greater effect on the likelihood of the training data, whether smoothing or the model will make a bigger effect. So therefore, we have insufficient information to determine which value will be greater or equal. And that's the final answer. Now let's move on to question 3. So in this case, we're considering the perceptron, where we have our input, our features x1 and x2, and there's also a bias feature, which is always 1. And then we have our weight vector w. And then through a linear classifier, we classify our feature vector, which is x1, x2, and 1, by taking the dot product with our weights and determining whether or not it's greater than 0. And if it's positive, then the classified label will be 1. Otherwise, it will be 0. So we are considering two cases, 2 features, and both of these features are binary. So we can write down just a quick table that will be useful later, where we have x1 and x2, and we can also consider our bias feature over here. So the bias feature is always going to be 1, and then x1 can be 0 or 1, and x2 can be 0, 1, 0, or 1. And then we want to consider, for these inputs, what our label y will be. So in part I, we want to determine which weight vector, which is w0, w1, w2, can classify y as x1, xor, x2, where xor is the logical exclusive operation, the exclusive OR operation, which equals 0 when x1 and x2 are the same, and 1 when x1 and x2 are different. So what the XOR operation would be is that when x1 and x2 are the same, it's going to be 0. So this is going to be 0 here, 1, 1, and 0. And we have some weight vectors. So we can see, like in the first weight vector, what this would do is that for the first case, it would multiply 1 times the bias feature, which is 1, plus 1 times 0, plus 0 times 0. So the result would be 1. So it would classify this training example of 0, 0 as 1. which is actually incorrect in this case. So we know that this feature vector won't work. And we can actually also similarly go through and see that these two feature vectors also won't work. And they won't satisfy that this should be the classified label for these examples, these feature vectors. And what we can actually see is that it isn't possible to compute this. And the way we can see this is by plotting our data right here. So our data is in 2D, and we'll say that x1 is on one axis and x2 is on the other axis. And we'll say that, well, okay. So if we plot each of our data points, first let's plot the negative examples. So one of the negative examples is going to be at 0, 0. And one of the negative examples is going to be at 0, 1, or at 1, 1. And then the positive examples are going to be at 0, 1, and 1, 0. So here's a positive example, and here's a positive example. And then what a perceptron is it's specifying a decision boundary between our data, and the goal is to find a decision boundary that separates the negative examples from the positive examples. And if it can do that, then our data is linearly separable. And we can see that there's no line in this plane that will separate the negative examples from the positive examples. And also, just something to note is what this bias feature allows us to do right here is without the bias feature, we could only consider decision boundaries that go through the origin. But now, because we have this bias feature, we can shift our decision boundary to be anywhere we want, any line in this space. But still, we can't, there's no decision boundary that will separate our data. For example, this decision boundary might correctly classify these two negative examples if the weight vector is pointing in that direction, but it would and it would also correctly classify this example, but it wouldn't correctly classify this example. So therefore, the answer is that no weights can compute this relation. Okay, so this column right here was XOR. Now let's consider the AND operation. So in this case, we want to find a y such that when we get 0 and 0, the result is 0, 0 and 1, the result is 0, 1 and 0, the result is 0, and 1 and 1 is the result of 1. So we only have 1 when x1 and x2 are both equal to 1. And what this would look like in the same picture we had before is we'll have a positive training example right here, and then we'll have negative training examples at the other three locations where this is x1 and x2. And we can immediately see that it is possible to separate these data. For example, if you had a decision boundary right here, that would, where your weight vector is pointing in that direction, then you can correctly classify and correctly separate the positive example here and the three negative examples. So let's figure out exactly which one of these options will work. So to look at this first option, we want to multiply it by each of our possible outcomes, which is the 4 listed right here, and see if it works. So with 1, 1, 0, if so let's make another table right here. We have our bias feature, so 1, 1, 1, 1, and then 0, 0, 1, 1, and then 0, 1, 0, 1. So with our first feature vector, which will say option A, we want to multiply 1, 1, 0 times 1, 0, 0 and add. So the result will be 1. And similarly, for the next example, the result will be 1. For the third example, the result will be 2. And for the fourth example, the result will also be 2. And so the resulting classification is that these are all going to be 1s because these are all greater than 0. And therefore, this isn't what we want in the AND operation, which is right here, where we want the first 3 to be 0s and the last one to be 1. So this one doesn't work. Okay, so let's cross that out. So now let's consider B. So let's compute the dot product for each one. We have negative 1.5, 1, and 1. So the first example will be negative 1.5. The second example will be negative 0.5. The third example will also be negative 0.5. And then the last option will be positive 0.5. So in this case, the resulting value of y will be 0, 0, 0, 1. This is exactly what we want for the AND operation. So therefore, this works, and we can select it. Next, if we look at the option C, we have negative 2, 1, and 1.5. So if we compute the dot product, we get negative 2, then we get negative 0.5, then we get negative 1, and then we get 0.5. So we get negative 2 plus 1 plus 1.5. And again, if we compare these to 0, we'll get 0, 0, 0, and 1 to determine y. So therefore, this option also works. So now let's consider the general case. We want to determine when we can get this outcome right here. So we can see that we can formulate some inequalities based on our weights in order to determine in what cases we will see this behavior. So in the first case, in the first example, where x1 and x2 are 0, and we want y to be 0, that means that we want w0 times your bias vector, which is 1, plus 0. We want that to be less than 0, because we'll have 0 times w1 and 0 times w2, and we want these result to be negative so that it's classified as 0. Similarly, if you have, in your second example, you'll have w0 plus w2, and we want this also to be less than 0, and we want w0 plus w1 to be less than 0 in the third example, and then finally we want w0 plus w1 plus w2 to be greater than 0. So what this first inequality looks like is we want w0 to be less than 0, and that's exactly given right here. Then second, we want w0 to be less than negative w2 if we bring this to the other side, and that's given right here. And this third inequality is w0 is less than w1, and that's given right here. And what the minimum does is it just says we essentially want w0 to be less than all of these quantities, which is the same as it being less than the smallest of these quantities. And then the last inequality is that we want w0 to be greater than negative w1 minus w2 if we bring these two to the other side of the inequality. And that result is given by this inequality right here. So therefore, this expression right here exactly is equivalent to satisfying all four of these inequalities right here. Oops. So this option is also true. The next question is to consider a multi-class perceptron with some initial weights that are given for WA, WB, and WC. And then iteratively we're given a feature vector and a label. So this is exactly how training works for the perceptron, is that we have our set of data, which is our set of feature vectors, and the labels that correspond to those feature vectors. And then in each iteration, what we do is we look at the feature vector. The first thing to do is to classify that feature vector. So let's add a column right here, which is going to be basically your classification. And the way you run classification for the multiclass perceptron is you take the dot product between the weight vector and the feature vector and pick the one that's highest. So if we do that for this first example, we will get a value of 1 here, a value of -2 here, and a value of 3 here, just by taking the dot product of each. And so the result is that WC will be the highest. So, or C will be the highest of the two. So the classified label is C. And therefore, because A is different than C, we need to update our weight vectors. And the weight vectors that we update is we update A and C, and the way that we update them is to add our feature vector to A to make WA more like f of x, and we subtract our feature vector from WC to make WC less like this feature vector. So the result will be that WA is going to be 2, -2, 3. WB won't change, so it will be 0, 1, 0. And WC, we will subtract the feature vector, so we'll get -1, 2, -2. Now let's consider our next feature vector. What we do again is we want to classify using our new computed weight vectors. So the dot product with the first one is going to be 2, -2, -6, which will give us -6. The classification with the second feature vector will be 0 + 1 + -2, which will be 1. And the classification with the third feature vector will be -1 + 2 + 4, which will be 5. So the classification here will be C. And again, this is incorrect. Now this time the actual label is B, and the incorrectly classified label is B, so is C. So WA won't change, it'll be the same as before, 2, -2, 3. We will add our feature vector f of x to WB to get 1, 2, -2 to make this weight vector more like our feature, because that's the ground truth label. And we'll subtract our feature vector from WC. So the result will be -2, 1, 0. Okay, now let's look at this last example that we have, where we have our feature vector and a label of B. So we want to classify it, and the dot product with weight vector A will be 2 + 2 - 12, which will be -8. The dot product with WB will be 1 - 2 + 8, which is 7. And the dot product with WC will be -2 - 1 + 0, which is -3. So WB will be the highest, the dot product with WB. So the classification will be B. Because these are the same, we don't need to update our feature vectors at all. So all the feature vectors remain as before with 2, -2, 3, 1, 2, -2, and -2, 1, 0. And that is the final answer.